It's the end. Okay, no, it's not quite the end. It is close to the end, and it is all about rank. So this idea of rank is going to come up again and again. And the rank is defined by the dimension of the column space of A. Remember, the column space of A, the dimension of the column space of A is the number of pivot positions or pivot columns or positions, number of pivot points, whatever. Doesn't matter. So the rank of A is also going to satisfy this equation. Hopefully this makes sense. The rank of A plus the dimension of the null space of A needs to equal the number of elements. So I hinted at this, right? In one of those examples, in the last section, it was a, you ready for this? It was a 1, 2, 3, 4, 5, 3 by 5 matrix. So A was a 3 by 5 matrix, which meant that it had 5 columns, which meant that it had 5 possible pivot points, 5 possible pivots. But we found that what did we come up with? We figured out that the column of A, or the dimension of the columns of A in that example, so this was one of the examples at some point, just roll with it. The dimensions of the column of A was 2. The dimensions of the null space of A was 3. And oh, look, 2 plus 3 was 5, right? And it kind of makes sense that the dimension of the null A is also the number of free variables. Right? So this is the number of free variables, and this is the number of pivot points. I don't know why I just did that. So hopefully it makes sense that the number of pivot points plus the number of free variables should equal the number of possible pivot points, or the number of columns. So this is the number of columns. Number of columns. All right. So if A is a 7 by 9 matrix and it has a 2-dimensional null space, that means, so this tells us that the dimension of the null of A is 2. What's the possible rank of A? Well, I have 9 possible columns, so n is 9. And if the dimension of null A is 2, n equals 9, rank of A should equal 7. Hey! All right. Now in a 6 by 9 matrix, is it possible to have a 2-dimensional null space? So this takes a little bit more thinking and a little bit more sort of mental gymnastics to really kind of come up with a thought process here. So let's assume, so if I have a 6 by 9 matrix, that would mean I'd have 9 columns, right? And what that means is that if the dimension, oh my God, oh yeah, it's getting worse, guys. If the dimension of the null space of A is 2, then the rank of A, so we're assuming it's true right now, would equal 7. But, there's a big button here, right? I might have 9 columns, but each of those columns, so each column only has 6 elements, right? So because it only has 6 elements in each of those columns, that means that I have at max 6 pivot points. By columns, I mean rows. Each column has only 6 rows. right? Which means that I have at max 6 pivot points, right? Because we find the pivot points by the leading position in each row in RREF or REF form, where I no longer have zeros in front of those things. So because of that, so I can only have at max 6 pivot points, which means my max rank is 6, but I would need to have a rank of 2, so that means no. I cannot have a 6 by 9 matrix with the dimension in the null space being 2. It would have to be 3 or greater. All right, the last part here in talking about the rank is just sort of combining all these ideas of basis and the column space and the dimension and all that kind of stuff and adding to our invertible matrix theorem, which turns out has been clutch for explaining everything, ever, just most of the time. All right, so the columns of A form a basis of Rn. Okay, so we've already talked about earlier in our invertible matrix theorem, we showed that the columns of A span. So the columns of A span Rn. So we already know that. So if that's true, and we already know that the columns of A are linearly independent, well, that is the definition of a basis for Rn. So that tells us that the columns of A form a basis for Rn. The column space of A is equal to Rn because if you remember, the column space of A is defined by, or the rank of that, here we can skip a little bit further, right? The dimension of that would be n, which means that I have no pivot points, or no free variables, right? So I have no free variables, which means that all of my columns are pivot columns. So all columns are pivot columns, which means that all of the columns are going to be included in the basis for R. So they're equal. Okay. The dimension, and then those say the same thing, right? We know that the rank of A is equal to the dimension of the column of A, so they both need to equal n, because again, we have no free variables. So then the null of A being equal to 0 means that we have no free variables. And if the null of A is only the 0 set, then by an earlier definition, the dimension of the 0 set is 0, so the dimension of the null space of A is 0. Ta-da! That's it. Okay.